This monolithic sphere resting inside a glass cube represents the historical limit of large language models. They've been confined to a localized generation box, waiting for user input before they can produce a single action. GPT 5.4 changes this role. It functions as an execution engine designed to operate native software and move beyond the traditional chat interface. Most modern agentic workflows fail because models cannot reliably manipulate graphical interfaces or process the sheer scale of modern tool ecosystems. We will deconstruct how OpenAI addresses these failures by examining the new visual parsing, its precise coordinate-based execution, and its architectural context efficiency. This upgrade specifically targets the technical bottlenecks that back-end software engineers and technical product managers encounter when deploying autonomous systems. OpenAI has officially equipped the model with the sensory and motor architecture required to operate the computer itself. Autonomous computer use requires the model to perceive a dense user interface without the loss of detail caused by image downsampling. This grid map illustrates the model's new original image input tier, allowing the ingestion of up to 10.24 million pixels of visual data. Previous models were limited to 2.56 million pixels, forcing data compression that caused agents to misinterpret clustered application interfaces or hallucinate buttons. High-fidelity perception provides the clarity necessary for spatial localization, knowing exactly where a specific button is located on a high-resolution screen. This chart shows OmniDoc bench performance, measuring layout prediction accuracy. The model's average error rate dropped from 0.140 down to 0.109. This visual clarity is the mathematical prerequisite for accurate coordinate mapping on dense professional software environments. This wireframe shows a vector point snapping to an XY axis. This is the mechanism for GPT 5.4's native computer use, coordinate-based clicking. The model issues direct mouse and keyboard commands in response to screenshots, actively navigating the DOM. The DOM, or Document Object Model, is the data representation of the objects that comprise the structure and content of a web document. To measure this, we look at the OS World Verified benchmark, the industry standard for testing an AI's ability to navigate desktop environments using visual inputs. On this benchmark, GPT 5.2 scored 47.3%, while GPT 5.4 reached a success rate of 75%. For context, the human baseline success rate for this specific test is only 72.4%. GPT 5.4 has moved past that threshold. Developers apply this by having models write code to operate computers through libraries like Playwright. Playwright is an open-source framework used for automating and testing web applications across different browsers. A new Playwright interactive capability allows the model to visually debug web apps and playtest UI changes while the code is being written. In a theme park simulation test, the model simultaneously generated art assets and wrote simulation logic, and autonomously playtested the UI to verify that guest happiness metrics were updating correctly. By achieving accuracy in desktop navigation, the model treats unstructured software environments as programmable APIs. At the API level, complex agentic workflows face a fundamental scaling problem: context bloat. This container shows the traditional method, where developers must inject thousands of JSON schemas into the initial prompt. A JSON schema defines the data types required for software communication. This results in a massive amount of input tokens. Loading contexts with thousands of unused tool definitions increases latency and significantly raises operational costs. GPT 5.4 introduces tool search. Notice the blocks vanish, replaced by a lightweight index line. When the model determines it needs a specific tool, it fetches the definition from the index and appends it to the conversation in real time. This economic shift is measured by the MCP Atlas benchmark, an open standard for tool connection. This split container shows tool search achieved identical accuracy on MCP Atlas while reducing total token usage by 47%. This level of efficiency enables the model to support up to 1 million tokens of context, facilitating massive, long-horizon data processing tasks. By removing the bottleneck of large toolsets, OpenAI made complex agentic systems viable for production. Long-horizon tasks carry high operational risk. If an agent makes an incorrect assumption early in a 1 million token run, the entire compute cycle is wasted. This timeline shows mid-response steerability. A cursor intersects the path and thens a vector, allowing developers to interrupt the model's chain of thought while working. Chain of thought is a reasoning technique generating intermediate steps before a final answer. This means a developer can inject corrections into a live financial model or legal analysis without forcing the system to restart the entire task. This level of autonomy requires safety verification, as reasoning models could potentially hide their true processing logic from monitors. OpenAI's new monitorability evaluations show that GPT 5.4 has a very low capacity for deceptive reasoning or obfuscating its internal logic. This lack of deceptive capability confirms chain-of-thought monitoring remains an effective safety tool for high-capability systems. Real-time steerability turns autonomous execution into a controllable, collaborative engineering process rather than a black box outcome. These geometric pieces snapping together represent the three pillars of GPT 5.4: high-resolution parsing, native execution, and dynamic context efficiency. These systems combined mark the maturation of the AI agent into a deployable API primitive. An API primitive is a fundamental interface or building block that allows for more complex software interactions. The focus of back-end development is shifting away from the optimization of localized, text-based prompts. Engineering efforts now prioritize the configuration of software environments and tool ecosystems that the model autonomously commands.